talk about more of this tomorrow. Okay. All right. So receive diversity is very simple. One of the oldest forms of spatial diversity. You basically have two receive antennas, one transmit antenna. So if these antennas are separated at distances large enough, okay, then the gains are more or less independent. So think about the situation where you put one antenna, two antennas separated by, say, a wavelength or half a wavelength, then the chance that both of them will be in the valley of your constructive destructive interference pattern will be small. And so the chance of both channels fading at the same time is small, and you get diversity that way. So if you look at the math turns out to be very similar to the math we use for the repetition coding. So in some sense, nature is doing the repetition for you. The same symbol x received at different copies of that at the different antennas. You can write that as y equals x plus w. And you can, of course, do match filtering. You can get a diversity gain. Here you also get a further gain. You get a power gain as well because you're having more antennas to suck up more power from your signal. So you get a power gain. It's a so-called 3 dB power gain with two receive antennas. Okay, power gain and diversity gain. Optimal reception via match filtering. In the spatial antenna language, this is also called receive beamforming. We will be a bit more careful about the word beamforming tomorrow, but here we use it in a very relaxed way. Okay, so the reverse problem is the transmit diversity. This is interesting. If you think about cellular application, then often your base station is pretty sizable. Your base station may have multiple transmit antenna, and you're interested in sending information downlink from the base station to the mobiles. The mobile may be simple device, only one antenna. Then you have this situation where you have two transmit antenna sending to one receive antenna. Okay, so you can write the channel this way. X is now a vector of symbols. So now I'm going to use vector notation without apology. X is a vector of symbols. H is the vector of channel gain. So you can write this as y equals hx plus w. Y is scalar. Okay. So what is the optimal strategy here to communicate? Okay. The optimal strategy here to communicate, if the transmitter knows the channel, so if the transmitter can have information about what the channel is, turns out the optimal strategy is in some sense dual to the receive strategy. Okay? So think about what the receiver does in the slide earlier. What the receiver does is it basically weights each of these signals by the complex conjugate of the number. So what you're doing here is essentially saying that you can measure the channel, so you know that the signal is received with a certain phase rotation at the two different antennas. You post-process the signal in such a way that your received signal, when you add it up, is added in a line fashion. So you post-rotate your signal to compensate for the channel, so that when you add it up in phase. And adding things in phase is a good thing. So when I teach this course at Berkeley, I teach them one important rule, one important formula. This formula is very important. This formula is the following. So I asked them, so these are Berkeley students, they're a bit slow. So I asked them, 1 plus 1 equals what? Okay, anyone knows?
3 dB.
How about in terms of normal numbers? All right, anyone knows? 1 plus 1 equals what? 2? Really? 1 plus 1 equals 2? Who taught you that? No, 1 plus 1 is not equal to 2. Not necessarily equal to 2. In this business, it's definitely not equal to 2. 1 plus 1 is equal to 4. Yes, it's true. And here's how. So that's exactly what receive beamforming or even transmit beamforming does. Okay? So if I add two complex numbers together, and I add it in phase, okay, then 1 plus 1 gives you a complex number of length 2. And so look, if you look at the power, then 1 watt plus 1 watt equals 4 watts. So 1 plus 1 equals 4. Okay? So that's the power of coherent combining. And that's what the receiver does. Essentially, the receiver says, we know the signals have been rotated by a certain angle. So I post-rotate it to compensate for it, so that when I add the signal up at the output of the 2 receiver antenna, they add up in phase, so I maximize my signal strength. And I get a 3 dB gain. So it's 3 dB gain because you would expect normally 1 plus 1 equals 2, but now you get 4. So 4 is equal to 2 times 2, 3 dB gain. Okay? And this is the receiver. At the transmitter, if you do the opposite thing, then a natural thing is now the transmitter, you do pre-processing. So you know that the channel is going to rotate with a certain angle. The receiver is dumb because it only has one antenna. So whatever nature adds up, it adds up. So what you do is you pre-rotate by a certain angle so that the signal add up in phase at the receiver. So what you do is you multiply by h, you normalize that, and you pre-rotate so that at the receiver, signals add up in phase 1 plus 1 equals to 4, and that's the optimal thing to do. Now this is phase rotation. There's another thing here, which is you also weight the signal. So you send a scalar symbol, you weight the signal by the strength of h. So typically you spend more energy when on the stronger channel than the weaker channel. So you do that together with the phase rotation. This is the optimal thing, transmit beamforming. And this is exactly the same performance as in the receiver case. All right? Y equals hx plus w. So from a math point of view, the problem is solved. From a math point of view, transmit, receive situation is exactly the same. However, from an engineering point of view, it's different. And the reason is because in many engineering scenarios, it's much easier to get channel information at the receiver than at the transmitter. So whereas the received beamforming, also called MRC, maximum ratio combining, you need to know the channel information, and that's often obtained by doing some training. At the transmit side, now there's something strange about this. How come I lost it? Oh, am I seeing things? Okay, strange. All right. At the transmit side, it's not so easy to get this information. Now, why is that? Let's think about a wireless system. Okay, in a wireless system, there are 2 types of wireless system in this world, basically. One is called, you're welcome, come in, time division duplex, and there's another type of system called frequency division duplex. So TDD versus FDD. Okay? So in a TDD system, an example of a TDD system is Wi-Fi, 802.11 system, TDD. You basically divide time into 2 types of time slot. One for transmission, and the other one for reception. So even time slot you send, odd time slot you receive. Okay? In a TDD setting, there is a good thing because there's a notion called channel reciprocity. If you think about the multipath situation, the signal going there and the signal coming back is essentially reverse of each other. So they go through exactly the same channel, which means that if your receiver can measure the channel, then you can use that information at the transmit side. So channel knowledge is easier to obtain in a TDD system. Let's think about an FDD system. In an FDD system, frequency division duplex, I transmit on a certain band, and I receive on another band. Okay? So for example, again, go back to our favorite system, CDMA system, IS95. The transmit, so typically when FCC auction spectrum, they auction FDD spectrum in a pair. Okay? Downlink and uplink, a pair of spectrum. Now, if you think about this pairing of spectrum, typically, where is this pair? So typically, it looks like this. So this is downlink from the base station to the users, uplink from the users to the base station. Okay? Now, the question is, how far are these two bands separated by? In fact, why are they not adjacent to each other? Why doesn't FCC just take a spectrum, cut it up into half, and just tell you to use uplink in one half and downlink in the other half? Anyone knows? I feel like walking in the audience and checking out who is sleeping and so forth. Sorry? That's right. So we have to think about the physics of the situation, right? You are a base station, right? You are sending information. You're listening to information at the same time, one on each band. Okay? When you're sending out information, if you compare that signal strength to the received signal, you're easily 100 or more than 100 dB off. Remember, signal propagate in space, so you hear a very weak signal, but you send a very strong signal out. So therefore, even the best filters that you can build cannot be so sharp that you would be able to attenuate the outgoing signal more enough, so that if these two bands are too close together, you'll never hear anything about the receiver, about the received signal. So this is the filter is called duplexer. Okay? So that's why typically these bands have to be separated very, very far apart. In fact, typical numbers 50, 60, 70 megahertz apart. Megahertz apart. Okay? So therefore, what does that mean in terms of the channel? Would you expect this channel and this channel to be the same? Yes or no? So what is a typical number for coherence bandwidth? Now let's go back to our numbers here. Delay spread. What's the typical number for delay spread? Microsecond. So what's the typical order of magnitude for coherence bandwidth? Megahertz, the reciprocal of that, right? So megahertz, maybe 1 megahertz or 2 megahertz, typical numbers. So with 60 or 70 megahertz, you'll be several, many coherence bandwidth apart. And therefore, the channel, in terms of the multipath property, will be quite different. And therefore, you have no reciprocity. And so, to get the channel information in the transmitter, you have to do feedback. You have to do feedback explicitly. And that's quite expensive. So a lot of systems do not have that. And so the engineering problem becomes how to get transmit diversity without knowing the channel information at the transmitter. Okay? So that's the engineering solution, the engineering problem. Okay? So that problem is got a lot of attention about, I would say, 10 years ago, 8 or 10 years ago. And it spawned off an entire field of study called space-time codes, which is essentially to design coding techniques to exploit the spatial diversity, transmit diversity, without knowing channel information of the transmitter. Because if you did know, then you don't need to do coding. You can do signal processing to do transmit beamforming. Okay? Now, how do we do that? Okay. Let me propose one method, and we will see whether we like it or not. Okay? So you have seen a pattern by now, right? The first scheme we always come up with when we want to get diversity is repetition coding. So let's start with repetition coding. Okay, so here is a way. I have a symbol X. I repeat it. I send it on another antenna X. Okay? H1, H2. All right? Okay. What about this method? People like it? First, do I get diversity of 2 using this method? Yes? Let's write down the equation. So the received signal Y is equal to H1 plus H2 X plus noise. Okay? So let's look at the Rayleigh case. H1 is complex Gaussian. H2 is complex Gaussian. H1 plus H2 is also complex Gaussian. So this has the same distribution as essentially Cn0, whatever. Okay? All right? So therefore, this is another flat fading single diversity channel. You don't get any diversity gain. The problem is that signals, they don't get resolved at the receiver. You look like you have two paths, but they all get combined into one path, one resolvable path. You have no resolution. So we got to try another thing. So I claim that repetition coding still works, but you have to do it slightly cleverer. How? Any suggestion on doing repetition coding, but with get our diversity? Time delay. So we don't have to be in a hurry. We shouldn't need to send the same symbol at the same time. So what I could do is I could send this symbol X, turn off this antenna, then the antenna, the receiver, will get a copy of X through H1. Then, so this is time slot 1. In time slot 2, then I send the same symbol X and turn off this antenna. And now I get a signal through H2. I receive at two different times, and therefore it's resolvable, and I get diversity. Okay? So I claim that this is exactly like the time diversity scenario. Okay? You can think of this, right? You can think of this is time 1. The mobile is located at this point. At time 2, he moved here. This is exactly the same as time diversity. The good thing about spatial diversity is I can get the same diversity without me moving. So if I'm not moving, the fact that I have two antennas simulate motion in some sense. Simulate motion. Okay? All right, so if we now think of this as a time diversity situation, then we immediately observe that repetition coding is rate inefficient. I'm sending one symbol over 2 time slot. Then obviously, we can improve that. So any time diversity scheme that improves over repetition coding automatically improves this scheme, because this is exactly the same as time diversity situation. So now I can send 2 symbol U1, U2, which is coded. For example, U1, U2 could be a rotated version of X1, X2, rotation code, and that will give me time diversity. Apply to this problem, that will give me transmit diversity. So any time diversity code you have, you can apply to this problem. Okay? And I would be able to get good rate and good diversity. The space-time codes, people say, okay, that's fine, but let's try to do something even more clever. Let me try to exploit the fact that I have 2 transmit antennae here, and I can actually send some stuff here as well. And then we came up with the first scheme. We solved this problem in a very elegant way, is the Alamouti scheme. So now we're, like right after lunch, people falling asleep left and right here. So I got to tell stories. So I got to tell you a story how Alamouti scheme came about. Do people know who Alamouti is? So Alamouti was at AT&T, your alma mater. Unfortunately, he was in, not unfortunately, a fact, he's in one of these development group, okay? Not your ivory tower research group, okay? He'd been in development group, have probably some spare time on his hands. So one day he thought, hey, why don't I do this scheme that I will be telling you about? And he said, hi, this is a pretty cool scheme. Let me show my manager. He showed his manager. His manager looked at the scheme and said, this cannot be right. Your scheme is so simple. First of all, it's either wrong. If it's right, someone must have discovered this before. So never mind, go back to your DSP coding or whatever, and spend more time there. And so he did. He put his scheme into his desk and not worry about it, until a guy named Taruk. So Taruk is in research, Ivory Tower, but Taruk is special because once in a while he goes to development groups and check out what they do and so forth. So he's a bit closer to reality. And then he talked to this guy, and Alamouti showed him, this scheme I had a few months ago, but my manager says it's kind of useless. What do you think? And then Taruk looked at it and said, man, this is good stuff. I can write many papers about this. And he did, and he did. And both of them got famous. So the moral of the story is don't listen to advisor in a school setting. Okay, so Alamouti scheme works as follows. Okay, Alamouti scheme says the following. It says that, let me change this to time slot 1, time slot 2. Alamouti scheme wants to send 2 symbols, okay, 2 symbols over 2 time slot, but instead of turning off one of the antennas, he sent full throttle. So every time he sends 2 symbols. So that matrix, okay, is the matrix of symbols that I sent. Okay, so if you look at that matrix, each column is a time slot. Okay, and each row is an antenna. So you first send U1, U2. We know it doesn't work just by itself because it doesn't get diversity. So what I do is I do coding. So the next time slot, I also send some function of U1, U2, but I send minus U2 star, okay, U1 star. So that's what it does, okay? So it sends 2 information or 2 symbols over 2 time slot. Okay, first of all, the rate is 1 symbol per time slot. So that's a good thing. That's a good thing. You don't waste rate. Let's understand the performance of the scheme. Okay. So we can rewrite. So now I write it in matrix form. Y1, Y2 is the received signal at the 2 different times. It's equal to the channel times this matrix plus noise. So I'm writing the equation for the 2 time slot all together now in 1 vector. Okay. Now I can rewrite this. If you think about it, so now what I want to do, I want to figure out what the channel does to U1, U2. So I'm going to write it in terms of some matrix times U1, U2. And you can do that. And it turns out that if you take the first equation and the second equation complex conjugate that, you get this equation. Okay? So now I'm expressing Y1 and Y2 in terms of some matrix H times U1, U2. And this matrix looks like this. Okay? It's just little one or 2 steps of algebra, and you get this. All right? So the noise is still complex Gaussian, same distribution. But now I have this matrix. Okay. So now what's happening? How do I decode U1, U2? Okay, how do I decode U1, U2? And if you look at this situation, if you look at the receive vector, now we think of everything in terms of vector. The receive vector is in general a combination of U1, U2, and it seems a bit tough to figure out how to recover U1, U2. But then, if you write down the picture, so what's the picture? The picture is that if you look at 2-dimensional space here, then I have a vector, okay, which is H1, H2 star. And I have another vector, which is H2, H1 star. The 2-column vector of this matrix. U1 is coming along this direction. U2 is coming along this direction. So you can think of it this way. All right? They interfere with each other, but Alamouti magic is that there's a special relationship between these 2 vectors. In fact, I'm drawing this in a purposely misleading way. Because these 2 vectors, if you take the dot product, you have H2 times H1 star minus H1 star times H2, 0. Okay, so these two vectors are perpendicular. And so I could detect U1, U2 by projecting onto this direction to get U1. There's no interference from this guy because this vector is perpendicular. So I can get U1 projecting onto this vector. And so I get exactly essentially the same performance as the repetition coding situation. But I can stuck in another symbol at the same time. So this is very clever, right? So I'm getting exactly the same performance as repetition coding, almost. Because I'm now the channel, the effective channel now depends on the norm of this vector. But at the same time, I'm sending two symbols over two symbol time. Okay. So that's right. When you project on two columns, you get this. Okay? So I am getting, very good. First of all, I am doubling the symbol rate of repetition coding. So I'm stacking two symbols at the same time. All right, so I'm doing definitely better than repetition coding. 2, the second point is, how do I do compared to transmit beamforming? So in transmit beamforming, I seem to get very similar performance. Right? I get this. So do I get the same performance? Not exactly. Why? Because remember in Alamouti scheme, this U1, U2 are two separate symbols that sent from each of the transmit antenna. For the same total power you burn, each of this symbol is half the power than the one that you would have used in transmit beamforming. So I double the symbol rate, but compared to transmit beamforming, I'm still a bit off. I'm 3 dB off. Okay, so I'm essentially have a 3 dB loss of received SNR. Okay, so think about why I lose this energy. In transmit beamforming, what did I do? I did 1 plus 1 equals to 4. Why? Because I can pre-rotate signal so that they add in line at the receiver. So in terms of energy transfer, I'm saying that, geez, I know where the receiver is. I'm sort of focusing my energy at where the receiver is. If I didn't know the channel at the transmitter, as in the Alamouti case, I don't know where to look. I don't know where the receiver is because I don't know what the channel gain is at the transmitter. So what I will do in Alamouti case is essentially send your signal in a omnidirectional way. So all your energy is sort of everywhere. And so you don't get this 3 dB gain, but you still get the diversity gain. And you still be able to send two symbols over 2 time slot. Okay? So the 3 dB loss in some sense is inherent to the problem and not to the Alamouti scheme. You can't, there's no hope of adding the signal in phase at the receiver. Okay? Is that clear? All right. Okay. So, all right. So you can generalize this to space-time code design. You can do essentially exactly what we did for the time diversity case. Okay? Remember what we did in the time diversity case? In the time diversity case, we developed a general criteria for how to choose good diversity codes by essentially looking at the product distance between code words. So here, in space-time codes, a code word is no longer a vector, but it's a matrix. Like in the Alamouti case, the matrix is U1, U2 minus U2 star, U1. Okay? It's a matrix. Matrix is space-time because the columns refer to space and the row refers to, as the other way around. The columns refer to time, the row refers to space. Okay? So you have a bunch of code words. And it turns out that the analogy of the criteria, the product distance criteria, is the determinant of xi minus xj times xi minus. This will be 0, isn't it? That's not good. See, this is a test whether after lunch people are still awake. I'm glad that someone pointed it out. x1 minus xj star. By the way, I've offered this course quite a few times, and this is the first time someone pointed it out. This is bad. This is bad news. Okay. I think I know why. I don't think I've ever lectured in a room with such a big screen. Okay. Xi minus xj times xi minus xj star. Okay. The determinant of that is the right analogy, generalization of the product distance. Okay. Sanity check. Sanity check. If I use a time diversity code apply onto a transmit diversity situation, then what can you say about the space-time code matrix? So if I send signals like this, at time slot 1 I send say U1, at time slot 2 and I turn off the other antenna. Okay, U2, 0. Then the space-time code has a special structure, right? What is that? It's diagonal. So the determinant of a diagonal matrix is what? It's a product distance. It's the product of the differences of the components. And so the product distance is a special case of the determinant criteria. So this is the famous Tarok product distance or determinant criteria. Okay. So let's move on. So this is essentially of course, there are a lot of papers written on this topic, but this sort of gives you the basic idea of transmit diversity. Okay. So now we move on to the another mode of diversity, okay, which is frequency diversity. So frequency diversity refers to what? So far we've talked about sort of narrowband channel which is flat fading. The way we get diversity is essentially over space so far, spatial diversity. Actually, even time diversity you can think of as a special case of spatial diversity, because the reason why we gain diversity is because we're moving over space. Okay? So therefore, now we're going to move on from spatial diversity to a different mode of diversity, and this is frequency diversity, and this occurs when you increase your bandwidth wider. So now you're communicating over a wideband channel. In a wider band channel, your channel may become frequency selective. In a time domain, that means, what does that mean? And that means the number of taps are greater than 1. The number of significant taps is greater than 1. So I have it here already. So I have L taps. Remember, HL is the gain of the Lth tap. Okay? That means the signal which are delayed by 1 symbol time will go through a gain of HL, H1, H2, H3, etc. All right? So this is my channel model. So now I'm not worried about time variation anymore. I'm freezing this channel. And now I'm going to get diversity over frequency. Okay. So again, there's an example of how I could get diversity through resolution of the multipath. So in a flat fading channel, everything sort of lumped up into one tab, and then they cancel each other, and I don't get diversity. When I have increased bandwidth, I start resolving these paths in different delay bins, and that gives me diversity over frequency. Multipath diversity is the same thing. So there are some books out there, not my book, of course, which says that, okay, there are many modes of diversity. There's frequency diversity, there's multipath diversity. Whoa, hold on a second here. Frequency diversity and multipath diversity is the same thing. Okay? So one is in the frequency domain, one is in the time domain, but it's the same physical reality. Okay, so all right, so let's start with a simple scheme again to get full diversity. How do we do that? How do we do that? Okay. Well, one approach is the following. Okay. Suppose I send one symbol every L symbol time. Okay. Okay. All right. So I send one symbol every L symbol time. So what happens is the following. I send a symbol X, At time 0, I receive H0x. Okay? At time 1, what I received? I received the symbols at time 0 multiplied by H1. Because H1 is the delay. It's the gain for the delay of time 1 symbol. And etc. And I'm saying nothing here. So all I'm receiving is copies of this x. So I didn't send anything for L symbol time. So again, I send x. So this is, let's say, x1. This is x2. All right? And so forth. So now I'm getting full diversity. Very good. Because I get L copies of this, I can combine them with the receiver. Again, maximum ratio combining or maximum match filtering. What's the problem with this approach? You should know by now, right? It's the same. The story repeats over and over again. When people watch Alon's video of this talk, they think, geez, there's something wrong with this video. It's repeating over and over again the same thing. There must be something wrong with it. But it's just me. Okay. We lose what? Right? We only send one symbol every L symbol time. This is essentially repetition coding. This is essentially the analog of repetition coding, except that the repetition coding in some sense, or this is like, it's like repetition coding. Okay. Obviously, we want to do better than that. Okay. What we want to do is, I don't want to waste these times. I want to keep on sending stuff at all times. Okay. So once you keep on sending stuff at all times, then another problem crops up, okay? Which is now I'm getting intersymbol interference. Why? Because now, if I start sending a symbol not here, but here, okay, then this symbol will go through H0 and hit here. The previous symbol is arriving at H1. So now the symbols start interfering with each other. This is the classic problem of intersymbol interference. Okay? So now I've got to deal with intersymbol interference. Okay? All right, so the challenge is really how do I deal with the ISI, intersymbol interference, while extracting the inherent diversity in the frequency selective channel. So the moral of the story is frequency selectivity is, in general, a good thing because it provides diversity to you. However, the ISI creates complexity, makes it more difficult to get that. Okay? So now we're going to deal with ISI. So if you look at sort of the history of communication systems, a lot of the work has been really focused on how to deal with this ISI problem. And there are essentially 3 approaches in the wireless arena. 1, time domain equalization, used by, for example, GSM. 2, direct sequence spectrum, used by, for example, local product, IS95, Cdma. And 3, OFDM, the new kid on the block. Everyone is doing that now. OFDM. The 3rd, 4th generation systems, a lot of them are now based on OFDM design. 3 approaches to deal with ISI problem. Let's go through one by one. Okay, so equalization means what? Means the following. Means that, look, the transmitter is really doing its thing. He's going to send symbols one after another. Okay? It's like, the transmitter is like Rudiger Abanke. Very relaxed, lying around. I don't want to do any work. I'm just going to send symbol whenever I want. Okay? The receiver is like me, working hard here, trying to earn the buck here. And trying to figure out, well, man, symbol X1 comes, X2 comes, all these interfere with each other. What do I do now? So the receiver is now working hard and trying to decipher the symbols. That's the essential time domain equalization. It's very unfair because the receivers do all the work. But hey, the world is unfair. Okay? All right. So that's what I'm going to do. In general, these symbols could be even coded symbols. In that case, the transmitter is actually doing some work. But let's consider extreme case where the transmitter is really a Benke, He's doing nothing. He's just sending, say, BPSK. One symbol, another symbol, third symbol, completely independent of each other. All right. Hey, by the way, this is videotaped, isn't it? Can we beep out the relevant words here? So, how do we decode? First of all, decoding is not that unmanageable. So Viterbi in 1967 came out with a paper which says, hey, you know what? The problem seems like a huge mess, but actually one can do an efficient algorithm to actually do the decoding. And this is the famous Viterbi algorithm. Everyone knows that. So that's not what I'm going to focus on. However, what I'm going to focus on is the following. If you do Viterbi, if you don't do any coding at the transmitter, can I get full diversity? Can I get full diversity? Right? So now I am in a good situation in terms of data rate because I'm sending one symbol per time. So my data rate is fine. But now I want to make sure at least I have good diversity. Okay? You say, wait a minute. First of all, there's no coding. There's no coding. All the other methods we talked about, space-time codes, time diversity, all involve some kind of coding of the information symbols to get diversity. Here, there's no coding. What hope is there for us? What do you think? Do people think I have any hope to get full diversity, even though there's no coding? The channel does the coding for you. What is coding? Coding is a way for you to introduce memory into the system so that symbols are interrelated with each other, right? All the other methods we talk about, the coding is done at the transmitter. But here, the channel itself has memory. So after you pass through the channel, automatically the received signal has memory. That is, the same symbol is actually contained in a lot of different received signal. So there's some hope of getting diversity. Okay? And there are lots of ways to do this, but we want to be fancy since we just learned about transmit diversity. So I'm going to reduce the ISI problem to a transmit diversity problem. Okay? Let's look at how we do the reduction. I'm going to create an artificial transmit diversity channel with L transmit antenna, where L is the number of taps in my ISI channel. In the first time slot, so I'm going to describe for you a particular transmit coding scheme, okay, which corresponds to what the channel did for me for the ISI channel. So at the first time slot, I send X1, okay, on the first transmit antenna and turn off all the other ones. So I received H0, X1. In the second time slot, I shift downwards and I send X2, my new symbol, in the first transmit antenna, and I send X1 in my second transmit antenna. And the channel gains here of my virtual transmit diversity channel is exactly the same as the taps of my ISI channel. Okay, so now you see the pattern. The received signal is going to be X1 times H1, the pass symbol, times the current channel, the one delay channel tap, plus the current symbol times the zero delay channel gain. So this is exactly an ISI channel if I continue. Okay? So I find suddenly that there are about like 8 people standing in the corridor here. Is there any space to fit these folks in here? Maybe some of you can move in. This is a fire hazard here, Maybe this place will burn down. We can't get out of here, and everyone is gone. Don't be shy. Don't be shy. There's some spaces. There's some spaces. Yeah, actually, there are quite a few seats over there. So don't be shy. I still have 2 more hours to go. So Okay. So All right, so this is my ISI channel version of the transmit diversity problem. Okay, so now, the you can ask, okay, what's the space-time code matrix for this channel? And you can write it down. And this is a space-time code matrix. So what does this mean? That means that if I send a particular input sequence, okay, then the space-time code matrix corresponding to that sequence for that particular scheme is this. So now my problem reduces to, and why is that? Let's think about it. Each column is a different time. So at the first time, in the first antenna, I send x1, and then I pop downwards, and I send x1 in the second antenna, at the same time send x2 on the first antenna, and so forth. So this is exactly the space-time co-representation of the scheme I described earlier, which create exactly the same effect as the ISI channel. Okay? So you can see that although I send my symbols uncoded, because of the nature of the ISI channel, essentially it is doing this transmit coding for me. Okay? It's essentially doing transmit coding for me. Now, so we can ask the question of whether we get full diversity is the question of whether I get full diversity in this transmit diversity scheme. So I think I forgot to mention it, but let's think about it. What was the condition to get full diversity in the transmit diversity scheme? I forgot to mention that. Let's think about it. Let's go back to the time diversity scheme. If you think of time diversity as diagonal matrices in a transmit diversity situation, what is the condition for full diversity? The full diversity means what? Think back at the rotation code, right? We basically want the vertical distance and the horizontal distances both non-zero for every pair of code word. That means you want the diagonal matrix to be non-zero, the diagonal difference matrix, to be non-zero in each of the components. That means you want a diagonal matrix to be full rank. So the general condition here for transmit diversity is you want the code word difference matrices. That is, if I give you two of these matrices, XA and XB, the differences between them should be always full rank. So that's it. Okay? So now it's easy to verify this. So if I take XA and XB, okay, if I look at the difference, then I can look at the first value for which they differ. So now you give me two sequences, XA sequence and XB sequence, and I ask myself, what is the difference between the two space-time code matrix corresponding to that? Then everything will be 0 until the first difference arises. Right? And the first difference arrives, I call it a time m star. Okay? And it looks like this. Well, this matrix is full rank. Why? Because look at all the rows. This row has a thing sticking out. It has zeros elsewhere. So this row is clearly independent of this row, and so forth. So all the rows are linearly independent. So this matrix is full rank. Very good. And so we're done. Okay? So therefore, Viterbi algorithm, that is maximum likelihood sequence detection, and uncoded transmission will give us full diversity. And also, I can send a symbol every second. So it's a good scheme. Good scheme. Nature is doing the coding for us. So I mentioned that Viterbi algorithm was efficient. It's efficient in the sense that the complexity does not grow or only grows linearly with the length of the sequence. In that sense, it's efficient. However, we all know that the complexity grows linearly in the number of states as well. And in the ISI case, the number of states is exponential in the memory of your ISI channel. So the complexity of Viterbi grows exponentially with L. So if L is small, that is for relatively narrow band channel, like GSM, where you have small number of taps, Viterbi is fine. But once I try to scale it up to broadband channels, wideband channels, like megahertz channel, then the number of taps will grow roughly linearly with the bandwidth. And so the complexity grows exponentially. So this approach of one guy working, this approach of doing time domain equalization really doesn't scale up to very wideband systems or wideband system. So like current 3G systems are all essentially wideband, 1.25 megahertz up to 5 megahertz wideband channel. So this approach is not adopted by any of those systems because of the complexity issue. So therefore, one has to think about a different approach. And let me talk about the Cdma approach first. Okay? So in a Cdma approach, you basically spread your information, okay, into the wide bandwidth that is given to you. So think about information sequence. You do some kind of channel encoding. You spread it by multiplying by some pseudo-random sequence, okay, and you go through a channel. So put some numbers here. In a classical IS-95 system, your data rate is like 9.3. 9.3, where's 9.3 come from? 9.6 kilobits per second. That's voice, one natural rate of voice. Your bandwidth is 128. No, 128, what I'm talking about. Bandwidth is 1.25 megahertz. My numbers are coming up completely wrong. 1.25 megahertz, okay? So the ratio between the data rate and the bandwidth is very large. It's 128. Save people from doing the calculation. 128. So this is so-called a processing gain. All right? So you have a very low data rate compared to your bandwidth. And this is a basic property of a spectrum system, Cdma system. Okay? All right, so this is a large processing gain system. Okay, so now the question is, how do I do equalization? Or how do I deal with ISI in this channel? There's still ISI, there's still potentially ISI. Okay? Let's think about it. Let's understand why I'm dealing with such system. So if you think about it, it's a very strange way of designing a system. I mean, my friends at Qualcomm are smart people. However, if you just think about it from a single user point of view, it's very wasteful. Because I'm using 1.25 megahertz to send 9.6 kilobits per second. I mean, this is very expensive. So obviously, I'm not doing this for one user. Right? I'm doing this for many users. So in some sense, Cdma only makes sense from a multiple access point of view. That is, you're using a lot of users to share this bandwidth. So essentially, you are in a regime where you have many users, everybody interfering with each other, and therefore, essentially, you're operating in a regime where the signal-to-interference ratio, or signal-to-noise ratio, is very low. So in a Cdma jargon, so unfortunately for us, every time we go to a new system, we have to introduce new jargon. But the jargon here is a chip. This is not a chip that you can eat, but it's just, in our jargon, a symbol. Okay? The signal-to-noise ratio, or in the Cdma context, signal-to-interference noise ratio is very low. So what you're doing is you're multiplexing many, many users together. They're interfering with each other. So typically a number would be minus 15, minus 17 dB per chip. Okay? So essentially you're operating at a very low signal-to-noise ratio regime. Your data rate is very low. Okay, so this is the way to think about Cdma systems. Low signal-to-interference noise ratio, very low per chip, but very low data rate. And you basically use coding to get back the information out, or signal processing, or both combined. Okay, so now let's think about this situation. And now let's think about ISI. How do we do ISI? How do we deal with ISI in this situation? Okay? So let's think back at this picture that we had earlier, right? So earlier, I say that if I send one symbol every L symbol time, okay, then I can have this symbol, and I can receive this symbol in isolation with other symbols. And I can do match filtering. In other words, I can combine the signal by multiplying by H0 star, H1 star plus etc. Okay, all right. So I can do so-called maximum ratio combining or match filtering to decipher my X1. Okay. So now I said, no, I don't want to do that. I want to sort of send at all times. But I'm operating at a very low signal-to-noise ratio regime, right? So in other words, the signal is low. The noise, whereas by noise I mean in the context of Cdma interference and noise, is huge. It's like almost 100 times. All right? Think about that. Think about that. So now, what do I do to do ISI equalization in that regime? Okay, so let's look at this. Let's look at X1. All right. So X1 is received in L components, right? On the other hand, I have interference from X2, X3, X4, and also from the past as well. Okay, so a lot of interference from other symbols. Okay, so now how do I try to what is the right thing to do to decode X1? Well, the right thing to do is to do some kind of Viterbi, right? The optimal thing. But I claim that in this problem, Viterbi is an overkill. It's a really big overkill. Because think about what the interference. Think about what is interfering with you. The other symbols are interfering with you. Okay? But that is insignificant compared to the interference and the noise from all the other users in the system. So you have huge amount of interference, right? We're operating at minus 17 dB. You have huge interference, and you have a little interference from your other symbols. But that's more compared to the other interference you're getting. So therefore, I shouldn't worry about it too much. I should focus on capturing the energy of my symbol, and that's the best I can do. And therefore, I should remain to do the match filtering. Ignore the interference. And the discrepancy is small. Okay? So, and that's the birth of the Rake receiver. So Rake receiver, unfortunately, every new terms every slide. All right? But the Rake receiver, and in some sense, the goal of writing a book is sort of try to give a unified view of that. The Rake receiver is essentially the receiver that people use in spread spectrum system, but it's essentially the match filtering receiver. And it's near optimal because the ISI is not significant compared to interference from other users. Okay? All right? So that's the, it took me a while, but I figured out why, an explanation of why Rake is near optimal. Okay, so this is a structure of a Rake receiver. You have a channel H, you match it with H tilde, which is the complex conjugate channel, and then you make a decision. Typically in a Rake receiver, you pass your decision through an estimator. You use a decision to estimate H, to revise your estimate of H, and you update this so that you can track the channel. Okay? So each tab of the match filter is a finger of the Rake. All right? Not the middle finger, but the other fingers, yes. The other fingers of the Rake. This is, again, videotaped, huh? This is not good. Maybe I should stop this videotaping. Maybe I should take back my... okay. Right. So each tab of the match filter is a Rake. So think of Rake fingers. Typically in a Rake receiver, these tabs move around because the paths may move around, and you're trying to search for the right fingers to match your receiver. So it's essentially a match filter, but with a time varying, you can sort of search the RAM. Okay, so that's it. So now we understood a second approach to deal with ISI. The approach of ISI essentially is that you design your system in such a way that you're doing multiple access with a huge amount of interference per chip at a very low data rate, and therefore the eyesight becomes not important. So you sort of design the eyesight out of the question. There is still eyesight, but it's not significant compared to the interference. Okay? All right. So now we go to the third approach. Both of the first two approaches is in some sense a lazy transmitting strategy. The transmitter is lazy. They don't do much. And so therefore, what you see is that